All right, so here we got a machine that fastens plastic screw-on caps onto the containers of motor oil. And it says if the machine applies more torque than the cap can withstand, the cap's going to break. And it says both the torque applied and the strength of the caps vary. The cap machine torque T follows a normal distribution with mean 7-inch pounds, or 70, I guess that means 7-inch pounds per square inch, I guess. And standard deviation of 0.9 inch pounds. The cap strength C, the torque that would break the cap, follows a normal distribution of mean 10-inch pounds and standard deviation 1.2 inch pounds. Okay, part A, what's the probability a randomly selected cap has a strength greater than 11 inch pounds? All right, well, it seems like a lot, but it's really not too bad. Let's first define our variables so we know what we got. Here we have that the capping machine has a normal distribution, and this is the mean of T is 7-inch pounds, so we'll say 7. So the mean torque of the machine. And then the standard deviation of the machine, the standard deviation of the torque, so the standard deviation of T is 0.9. Now we have the machine that tights the motor oil containers. Then we have the cap strength, individual caps that can withstand torques. So that's the piece on the oil container. That's going to be C. It says the mean of C, the mean cap strength is 10 inch pounds, and its standard deviation of C is 1.2. It's also normal. So we got that so far. But we're trying to find the probability, part A, the probability that a randomly selected cap has a strength greater than 11 inch pounds. So we want to find the probability that C is greater than 11. And so we're going to be looking at this distribution, the mean of 10 and a standard deviation of 1.2. So we have, let's draw a little normal curve sketch. Mean of 10. Normal. So n of 10 comma 1.2. And we're trying to find the probability that C is greater than 11. So we're trying to find essentially the area to the right of 11 here. Okay, so essentially you're just going to find the z-score that corresponds to 11, since this is a normal distribution, and then find the area to the right of that z-score. So remember, z, the general formula for z is equal to your observation value, x, minus the mean over the standard deviation. So we look for the z value that corresponds to this 11. So then we would have that z would be 11 minus the mean minus 10 over the standard deviation, 1.2. You're going to have 0.83 repeating. So again, we're looking at a normal distribution, or the standard normal distribution, where the mean is 0 and standard deviation is 1. We're finding the area to the right of 0.83. So reviewing back with you what you learned in chapter 2, in case you need a little refresher. And so you can use table A to look for the z value closest to 0.8 or 0.83. So we got 0.83, and we have an area of 0.7967. Now remember, this 0.7967 is the area to the left. So we have an area of 0.7967 on this side. So it's like this light area, that's 0.7967. That means the shaded area will be 1 minus 0.7967. That'll be about 20%. So about 20.33%. 0.203. So the probability that a randomly selected cap will have a strength greater than 11 inch-pounds is going to be about 0.2033. So that's part A. We got part A down. Part B, explain why it's reasonable to assume that the cap strength and the torque applied by the machine are independent. So what they're getting at is kind of like, why are they asking that? What they're getting at is because in the next parts, you're going to be combining random variables, and in order to apply the techniques of adding and multiplying and calculating the variance and the differences, you have to make sure that the variables are independent. So that's why they're tying that in. So you just say, like what you would think in real life. Say, it's because, they're different machines. The torque machine, the machine that's applying torque is different than the machine that's, creating the caps. So, because they're being made by different machines. Made by different. I'm just squeezing that in there. I don't know why, but this isn't the important part. Is not the actual answer. The important part is you understand that these variables have to be independent for us to do the next parts. So in part C, we have that the random variables d is defined to be equal to c minus t. So we want to find the mean of d and the standard deviation of d. So d is basically the difference of c and t, the difference of two random variables. So the mean of d is simply going to be the mean of c minus the mean of t. That's just a property of the differences of random variables. When you're subtracting two random variables, the mean of the differences is going to be just the differences of their means. So the mean of c, 10, minus the mean of t, 7. So the mean difference, mean of d will be 3. Standard deviation of d, you're going to have to find the variance of d. Remember, the variance is standard deviation squared. So standard deviation is just the square root of the variance. So we have to find the variance of d. And the reason is because you can't simply find the standard deviation by adding or multiplying or subtracting standard deviations. It's not going to be that simple, but it's easy to derive once you know the variance. So the variance of the differences of these two variables is actually going to be the sum of their variances. The variance of d is going to equal the variance of c plus the variance of t. It's going to be counterintuitive. It's going to be kind of like, how does that make sense? But it does. And I go over it in a previous lesson, but it's essentially because this is a measure of spread. Now, it doesn't matter if you're looking at differences or sums of values. Spread is spread. How far away is how far away, regardless if you're adding or subtracting. Anyways, so we find the variance of d. Variance of d will be the standard deviation of c squared, which will be 1.2 squared. The standard deviation of t squared, which is 0.9 squared. Get 2.25. .25 is the variance of d. And so the standard deviation of d will be the square root of 2.25, which will be 1.5. Standard deviation of d will be 1.5. All right, now in the last part, we're finding the probability that a randomly selected cap will break while being fastened by the machine. What's the probability that some probability that the machine's going to break the cap? Okay, the torque is so. In other words, what's the probability that torque is going to be more than the cap can withstand? So RD, we want to find the probability that C minus T is going to be a negative number. Okay, so let's think about this. Remember, it's going to break if the value of T, the value of torque, is more than the value of the cap. Because if the torque is more than the cap strength, it's going to break. So then we want to find the probability that C minus T is less than 0, is negative. That's the same as just find the probability that D is less than 0, because we found that we made D equal to C minus T. So we want to find the probability that D is less than 0. And wow, coincidentally, we already got the mean standard deviation of D. So we're looking at this distribution. Distribution of D is approximately normal with a mean of 3 and a standard deviation of 1.5. So we find the probability that D is less than 0. So if 3 is there, 0 is going to be somewhere over here. We got to find this area, the area to the left of 0. And so again, we use our z-score. We find the corresponding z-score for this. Again, we use a formula, x minus or mu over the standard deviation, but in regards to this, our observation value is 0, so 0 minus the mean, 0 minus 3 over the standard deviation of 1.5. We get negative 3. Well, obviously negative 2. So we're looking at, again, now we're looking at a standard normal distribution. We'll sketch right here. Mean 0, standard deviation of 1. We standardize our value, made into z-score. Mean of 0. And we're looking at the area to the left of negative 2 on the standard normal curve. So go to our table A again, and look at negative 2. And right away, negative 2.0, we have an area of 0.0228. Now we don't have to subtract because it gives you the area to the left. So right away we find it that's negative, or that's 0.0228. So this area is 0.0228. So the probability that a randomly selected cap will break while being fastened by a machine is going to be about 2.28%. So our table change it. You have to change this percent, but 2.28. And there you go. That's all there is to it.